Welcome to a new video about LC ladder filter design. This is an example about a Chebyshev response where we design a low pass filter. We will specifically look at the situation where we have an unmatched source load configuration. We have seen in the previous example about the Butterworth response where the source and the load were not equal, so they were unmatched. And this is the situation for the Chebyshev response to illustrate the concept also there. So we will see how we can calculate the components values for this circuit. And we will see how we can also calculate like the low frequency gain for this specific situation. Of course, we will work out everything in our calculations step by step and also verify these in SPICE simulations. Okay, this is our objective. We would like to design a Chebyshev response with a passive LC ladder configuration. It must be a low pass filter. The final design must have an RS of 10 ohms. That means the source resistor and the load resistor must be 40 ohms. So you see already that these are not matched, or they are not equal. The specifications, the maximum passband ripple, it must be 1 dB. So we know that the Chebyshev response must be from a 1 dB ripple, because you have also different ripple characteristics of the Chebyshev response, like the 0.5 dB or 2 dB. The minimum stopband attenuation we want is 20 dB. The maximum passband frequency is 1 megahertz, and the stopband frequency is 2 megahertz. Okay, let's see what we need to do for our calculations. First, we start always with the first filter order N. Now we know that we need to convert the passband ripple and the stopband attenuation to a scalar value. In this case, we start with the epsilon p to relate that to the Amax. Amax is 1, so we can calculate that using this formula. Will give us 0.5088. Epsilon s is related to that stopband attenuation using that A minimum. A minimum is 20, so you can substitute that here. You get here 9.9499. Now taking these together in similar formats we have done for the Butterworth response. In this case we have a different formula, and we have now again epsilon s and epsilon p, and also now here the stopband and the passband frequencies. Now when you substitute the values here, 2 megahertz, 1 megahertz, and also the other values we just determined, you get here 2.7834. So we need to go to an integer always, so we need to take n as 3. So we need to design a third order Chebyshev response filter with a ripple of 1 dB. Now this is the Chebyshev response 1 dB ripple for a third order configuration. You see here the LC ladder low pass filter configuration. We're having the normalized elements, and it is now double terminated. So what you see is there's a ratio between the RS and RL. If, for example, RS and RL was exactly equal, so that means RS over RL is 1, then you need to use these normalized values. In our case, we have RS over RL is 10 over 40, because that's the final design. That means we need to have it 0.25. That is actually this. So we can actually look at it, that we need this row. And that means we need to use these 3 normalized values for our final design. Okay, that's important. That's distinctly different than the case where you have the matched source and load configuration. So step 2 is calculating the frequency scaling factor. This is also the cutoff frequency for the Chebyshev response. That is related to the passband frequency, but using the formula which converts the passband frequency into the cutoff frequency, which is given by this formula. You see here the filter order and also the passband scaling here for the passband ripple, and also cosine hyperbolicus and also the inverse cosine hyperbolicus. So we just substitute here the 2 pi times the fp and also the n, which is 3, not this one, of course, this, and also the the epsilon p. So we do that, and what you have is then the value of 6.879 mega radians or million radians per second. Now this is what we need to use as the scaling factor for the frequency. Okay, step 3 is calculate the scaled component values. These are the normalized low pass filter configuration we also have seen for the Butterworth response, so that's also the same for the Chebyshev, and we need to scale this up to these prime values. This will be in the final design as said 10 ohms. This is then 40 ohms, but now we need to also determine the C1 prime, L2 prime, and the C3 prime. Calculate now the C1 prime, which is our scaled up component value for the capacitor C1. That is then C1 from the table. We see here 8.8619, but here over the magnitude scaling factor and the frequency scaling factor. The magnitude scaling factor Km is 40. The reason for that is that we have a load resistor of 40. So the load resistor here is considered in the normalized value 1. So in order to go from 1 to 40, we need to have a magnitude scaling factor of 40. The source resistor is considered to be 0.25. So you have 0.25 over 1, which is also the ratio here. You see that RS over RL is 0.25. That's the reason for having this KMF 40. Now that will give us 32.21 nanofarads. The L2 prime, which is related to again the magnitude and the scaling factor for the frequencies in this form, and also with L2, which is normalized value, we take it from the table here, 0.6799. And that will give us this value, and a C3 prime in a similar form, but then we'll get this normalized value in a similar form as we have done for C1 prime. So for RS prime and also the RL prime, we use the 40 times the 0.25 for the RS, because this is the normalized value here, 0.25 ohms, and here it is 1 ohm. So you can actually see here the final values appearing as we wanted in the final design. So the designed circuit, you see here also here the prototype filter, which is unscaled. So you see 0.25 ohms. You see here the components values as we have it from the table here, and this is 1 ohm for the load. This is now scaled up, 10 ohm for the source, 40 ohm for the load, and you see here the C1, L2 and the C3 as we have to calculate here. So this is our final design. And we will now check the final design in the body plot. This is now the magnitude response for the body plot. For this circuit, you recognize here the low pass pass band gain. This is actually a low pass characteristic. You see a ripple, by the way. You see here, because it's a third order, you see a ripple here, actually a valley, and a peak, so one valley, another peak here. And there is also a ripple part here, so it's actually a third order. This is the characteristic of a third order, so you can actually count the number of peaks and valleys in order to determine the order of the Chebyshev response. The passband gain is minus 1.938 dB, which is a low frequency gain of 4/5. Why? Because if you look at this, at low frequencies, the capacitors are open and the inductor is a short, so that will be 40 over 10 plus 40. That means this will be then our gain. And if you convert that to dBs, you get now here 20 log of 4/5 or 40 over 50. So you get minus 1.938 dBs. So that's correct. Now let's also have the situation at 1 megahertz, because at 1 megahertz we need to have a maximum ripple of 1 dB. That means the following: the baseline was here minus 1.938 dB, and we go down here at 1 megahertz to minus 2.933 dB. This decrease from the baseline to this value at 1 megahertz is less than 1 dB, because that's also called the maximum passband ripple. So this is exactly as we wanted. So it is lower than the ripple here maximum allowed. The next one is about the 2 megahertz. At 2 megahertz you see here a gain of minus 24.39 dB. Now from the baseline we go down from here this value to minus 24.39 dB. That is a difference of 22.45 dB. And we need to have a stop and attenuation of 22 dB at least, so we get that. So that's also achieved. So in summary, we can say that this is all met. So we have met the specifications here. Let's also give a table as a summary for the designs we can make later for the Chebyshev response, in this case just for 1 dB ripple. These are the normalized element values in our LC ladder filter configuration. You see here the filter order N2, N3, 4, 5, 6, 7. There are of course 8, 9, 10 and 11 if you want, but this is for now the presented version. We have here again the ratio between RS and RL. So RS over RL, that is in this case 3 for example, then you get these element values. If it is 4, you get these element values, and you can also look at the third order, fourth order, 5th, 6th and the 7th order. The circuit you need to use for the 2nd and the 3rd order are shown here. This is for the 2nd and the 3rd. You see here the order also, C1, L2, and C1, L2, C3. So this is actually X1, X2, and X3. For the fourth and the fifth order, you see actually again the circuit here. And for the sixth order, this one you have 6 elements, 6 reactive components. And you have here 7 reactive components for the seventh order. So C1, etc. This was our example considering the Chebyshev response with a 1 dB ripple, having unmatched or unequal source load configuration. If you have any questions, comments about this example, please let me know and I will try to answer them as soon as possible. Don't forget to like and share these videos so that we can reach more people for these interesting topics. More about the LC ladder filter design, you can look at the playlist in the description of this video. See you next time in another video.